Greetings, Earthlings. So the 2.5 function transformations. Vertical shifts, we're all good with this, I'm hoping. So if you're starting with x squared, it doesn't matter what the shape was, but we're using x squared. But if it's whatever the original function is, you just slide it up 2, right? So 1, 2. And if the function is, I guess I'll leave that one there. Down 5, 1, 2, 3, 4, 5. Now most people tend to look, if you have a quadratic, at the vertex. Could you have chosen any of the points? Slid it down 5? Just keep that in mind. Because sometimes you'll be asked a question like this. Now maybe the function has a point right here. And I'll say this is from f of x, right? 2, or what is this one? 7, 3 is a point from f of x. What happens when you apply this transformation, f of x minus 5? Well, you'll say that goes down 1, 2, 3, 4, 5 to become 7, negative 2, right? We're all familiar with that. Okay. So the conclusion here, f of x plus k is a vertical shift of k units. The sign is the same. If it's plus 5, it's up 5. So, and like I was saying, if you're just given a point of 2, 4 belongs to the function, then f of x plus 1 changes that point by going 2, 4 plus 1. 5. Okay? No questions there, I'm hoping? No? Okay. And horizontal shifts? Think of it as f of x minus the shift, right? When I see x plus 3, I'm thinking x minus negative 3, right? So when I do that one, let's start here. Yeah. F of x plus 3 is really minus negative 3, 1, 2, 3. Right? And f of x minus 5 is that subtracting positive 5. So it should look like that, right? So our conclusion, very similar to the other one, except this is horizontal, right? X minus h. And we tend to use h and k for those. Sometimes p and q, depends on the textbook. It gives a horizontal shift of h units. So if 2, 4 belongs to f of x, then f of x plus 3, I'm thinking that's minus negative 3. So negative 3 is what works on the x value, right? So that's 2 minus 3. That's where you get the negative 1, 4. Okay? Whether you're given a picture or not. And some of the other things. I'm calling this 3 and 4 here. Vertical stretches and compressions. So what if we had this? X plus 1 all squared multiplied by x minus 1. What? F of x. 3 times f of x and 1/3. So stretch and compression, squeeze, right? So let's just take a look at this here. So here's the original function. Good. When you multiply everything by 3, it does nothing to the zeros, right? It just stretches. This dip here goes 3 times as much. Everything's stretched by a factor of 3. This, you can't see it very well, but this grows 3 times faster in a sense too. When I put 1/3 there, the zeros remain the same. It's just now, this part here is 1/3 the depth that it was. This grows at 1/3 the original rate. Okay, so I'm hoping there, that's not news to you. A term in front of f of x. If it's stretched, if you got a number in front of it other than 1, it's stretched by a units. And compression if it's 1 over a. If it's smaller than 1, you could have like 2/3, right? It doesn't have to be 1 over a. Okay. I won't get into that. I was going to say, well, 2/3 is correct. It's 3/2 units. But anyways, now the accordion, left, right, horizontal compressions and stretches. That's 5 and 6. you're used to seeing this usually with the sine function. So, sideways s for 0 to 2 pi, right? What happens here? So that's the normal function, 1. As soon as we put a 2 inside there, you get twice as many things, one complete cycle in half the amount of space, right? Likewise, if we put a half in here, in that same 0 to 2 pi space, only half of a complete cycle occurs. It's a reciprocal effect, right? Takes 2 times the length now to complete a full cycle. Take 4 pi. So, as you've seen before, f of b of x is compressed by a factor of b. Here's where it gets tricky. You got to sit and think about it sometimes. So, if 12 comma 5 belongs to the original function, then f of 3 times x changes that point to a third. The x value of 12 divided by 3 is 4. Y values remain the same. Okay, and then a graph of 1 over b, so something like 1/3 or something like that, stretches horizontally by a factor of b. So if we apply 12 comma 5 as the original f of x, a point in the original function, 1/3 x, that changes on there, f of 1/3 x, 3 times. This same point will be stretched over 3 times. Okay? Now this isn't news to anybody, right? Reflections about the x-axis. Positive f of x is your given function. If you reverse the sign in front of it, well, you see how that works, right? You reflect in the x-axis. Here's a specific example. I didn't need to give you the equation, though, to see how this works. Okay, reflection about the x-axis when you multiply it by -1. About the y-axis, f of x there, if you put the negative sign inside the bracket, it works on the x coordinates. You reflect about the y-axis. This is your mirror line kind of thing, right? Bob, do you need to get up and take a quick walk, or are you going to fall asleep on me? Okay. There's an example specific. Okay, where am I now? Boop-de-doo. All these changes. Well, let's just play around with some of these things here. On the left, I have the originals, the W. Okay, so all of these transformations combined into one function as well. We'll do science questions as a group here, the first few. We'll see what we need to know after that. So I'm going to give you guys a little bit of time. You take a look at these. We'll see. What's the trick? No, what we're supposed to, well, okay, yeah, match. You can look through these. All of the answers, 25 through 36, are given for A is one of those numbers. Yeah. I wouldn't do it as matching no more. Look at this and think, okay, what has happened here? It looks like the shape is the exact same. It isn't warped. It's just slid up too, right? So then, I'm going to say, I hope you have g of x plus 2, right? So continue on with these. I'll give you guys a minute.